Okay, everybody, Dr. D here again. This is our Chapter 16 video. This is additional aqueous equilibria. The acid-base chemistry of 15 was our initial aqueous equilibria topic. Now this is additional concepts. The first thing I want to talk to you about is something called the common ion effect. And while this is not exactly the same as Le Chatelier's principle, the reasoning really behind it is the same. The idea here is if a common ion is present, already in solution in which we're trying to add more of something, then that will inhibit the forward reaction. So for instance, if HCO3 negative is present, that will inhibit the forward reaction. That's the common ion effect. So you can see that it's very similar to Chatelier's principle, as if I have a system in equilibrium and I add HCO3 minus, it's going to form more reactants. So what we're saying here is now, and we deal this with only ions, so it's specific about ions, but it comes in handy if you're trying to dissolve something in solution. Say I'm trying to dissolve barium sulfate, and I already have water that has sulfate ions in it. Maybe it's got sodium sulfate in there. It can't just have sulfate ions, of course, because you always have to have compounds. Electroneutrality, if there's anions present, there has to be cations present. I'm trying to dissolve barium sulfate in a solution that has some sodium sulfate already. My solubility will be less than if it was in pure water because of the sulfate ion already present. And that's really all the common ion effect is. That's really all I want to say. Now, pH buffers is a pretty big topic, but we don't do a lot of what's in Chapter 16, as you'll see. This video will be on the shorter side. There's several sections we don't cover in 16. Buffers is a big section, but we're not doing any of the calculations related to buffers. So all I want you to learn is what a buffer is and how you would choose to make up a buffer and where its kind of its capacity comes from, like how much it can buffer. So its buffering capacity and the extent, the range at which it can buffer. That's the important thing I want. So it's a solution that resists changes in pH. Basically, when small quantities of acid or base are added. And the idea is to make this up, you want to use like a weak acid or a weak base, and then the conjugate of that. Okay? Its conjugate partner. So, for instance, acetic acid, classic weak acid. You would use this and this, the conjugate partner, but you can't just add acetate ions. I have to go to my shelf in my chemistry lab and get a compound. So a salt, I would just add sodium acetate. Now the idea here is that it will use this to represent the acid and the base, A negative, like we always do, HA and A negative. Well, that came out terrible. Okay, so the idea here is if I have this present in solution and base is added, well, I can neutralize the base by forming H2O plus A negative. And if I have A negative present, I can neutralize any acid that's added by forming HA and H2O. And you want a weak because a strong one will simply dissociate and acidify your solution. So that's why it has to be weak. And you might wonder, well, why can't I just make it up just from this? That'll give me the acid and some of the conjugate base. I don't have to worry about adding this. Well, the problem is you wouldn't have enough of this in solution, A negative, because this is weak. So that's why you add the salt. So you often add them in equal quantities. So you have roughly the same. Now, there might be situations where you want to buffer more against an acid than a base, and you might have more than one or the other. But in general, they're pretty much present in equal quantities. And this allows the pH to go unchanged. And you see this in this figure here. For a particular buffer, the pH doesn't change that much. stays fairly close to 6.5, even if we add a large amount of base or a large amount of acid. Or I shouldn't say large amounts, because that's where the capacity comes in. How much you can add is dependent specifically on the concentrations of the weak acid or base and its conjugate partner you add. So that's the capacity. Here's the sodium hydroxide added, and here's kind of the the amount of material that you're putting in. And you see the change of pH here. The higher the concentration, I forget exactly what this notation is in the books with the 75x, 50x, but this is basically the higher concentration. Oh no, this is the lower concentration. Buffer A, buffer B. This is the sodium hydroxide added. So the more sodium hydroxide added, based on the buffer, we're not really even talking about the amounts added here. There's nothing indicating the amounts of the buffer added. But the more base that's added, the greater the change. And you can look at your textbook and what the difference between buffer A and buffer B is here. I can't remember. So that's your capacity, quantity of acid or base that buffer can neutralize by maintaining pH. The range in which it can buffer around is how close you are to the pKa of the acid used or the pKb of the base used. So for instance, if I want to buffer around a pH 5, I got to make sure that I choose an acid that has a pH close to that, because I'm only good at buffering about 1 unit on either side of the pKa or pKb. Okay? So if I'm trying to buffer at pH 5, I'm not going to use an acid that has a pKa of 6.9. Right? So that's the whole idea. So that's the range in which you can do it at. And here's the pH change. This is what I was thinking about here of a buffer versus the buffer concentration. So here's the buffer concentration on the x-axis, and you have a high buffer concentration. You stay close to that buffer pH, even so we're adding HCl, which is going to lower the pH, and we're adding sodium hydroxide, which is the base, which will lower it. So if you have a low concentration and you add some sodium hydroxide, you can see the pH is increased quite a bit over the desired buffer pH, or if you add HCl. But with a high concentration, we get very little change in that pH. The other big topic in your book is titrations. Again, we're not going to do a lot of the calculations. I'm going to do one calculation in class with a titration, which is kind of like a neutralization. That's what titrations are. You're kind of neutralizing them to an equivalence point. So what you typically do is you might have a beaker, and I'll show this. There's a figure over here, actually, of a titration. So the titrant is what you're putting in the burette. It's been standardized. You know its exact concentration. That's what you're adding to your beaker, which is your unknown. Okay? So let's say our beaker is an acid, and we're trying to figure out its concentration. We'd have a standard like sodium hydroxide solution as our titrant. And we're going to add enough sodium hydroxide to neutralize that base that's in the beaker. That's the equivalent point when they're stoichiometrically the same. So what you can do by knowing the titrant, you can figure out what's in the beaker, which you might not know, because you're going to know what the concentration of this you used is. You're going to know the volume of what you used because you're going to measure it from the burette, and you're going to know the volume of this because you're going to measure it out accurately. The only unknown will be the concentration of this, which we can determine mathematically. pH meter is ideal to be used, but lots of times we use indicators. And indicators can help you find an endpoint. And it's important to realize that an endpoint is not an equivalence point. The equivalence point is the stoichiometric. The endpoint obviously needs to be very close to that. That's the whole idea. And when you look at titration curves, you'll realize that the difference between the endpoint and the equivalence point is usually so small volume-wise that to 2 or 3 sig figs, it's not going to make a difference. So you don't worry about that. But what you're going to be looking for is a color change. So you'll choose an indicator based on what you expect as far as your equivalence point is going to be. And you'll see the range of colors for those indicators. So a titration then, you've got, this is a nice digital one, pH meter here. And here's your burette. Where you're going to use indicators. You're going to look for changes in color in the lab. Known volume to the beaker. Few drops of indicator. Your burette with that standard solution, slowly. Good people that do good titrations have patience. Okay? Never been one of my high qualities, so I've never been a good titrator. Sometimes you need to drop literally a half a drop to hit the end point accurately without overshooting it. So you got to be very patient. You can't go through too fast. Here's a strong acid-based titration. This is the only one I'm going to talk about even in lecture. And it has a very steep curve, as you can see, where the pH changes dramatically with barely any addition of volume. That's why the end point and the equivalence point, the slight difference there is not going to matter, because you're talking about, 10% of the actual drop that you add. So the volume is so small. So what you'll notice is with a strong acid, strong base, the equivalence point will always exactly be 7. Okay, I'll talk about that. There's a little bit of a little bit more advanced chemistry to understanding that. But for right now, as far as the video goes, you can see this is very steep. And this is I'm adding sodium hydroxide, so I'm starting out with an acid in my beaker, and initially the pH doesn't change much. When you start to see it get higher, that's when you got to slow down in your titration and do only a drop at a time, or you'll overshoot it and miss your equivalence point. But it's important to realize it's 7 only for strong, whether you're titrating a strong acid with a strong base or a strong base with a strong acid. If I titrate a weak acid with a strong base or a weak base with a strong acid, the pH is not going to be exactly 7. The reason is, which I'll explain in lecture, is exactly the same as why we saw in chapter 15 there are acidic and basic salts. The chemistry is the same. It's what happens in solution with those species you're creating from the titration that'll determine what that final pH is, and that's something I will talk about in class. 2 other things left. One is to introduce solubility equilibria and treat this the same as we've always treated it, a rice table. This is products going to reactants. We want to know what the concentration of these are in solution. If I dissolve as much of this possible, that's the solubility. So I know it's soluble, so I'm going to have some solid left at the bottom of my beaker, which means the solution will be saturated. The question is, what are the concentrations here? Well, you can realize that this is not going to be included in equilibrium expressions. That's solid. These are going to be basically, right, plus x and plus 2x. So at equilibrium, there'll be x and 2x. And then you put them into the expression, you get x and 2x squared. You solve for x. That will be the solubility. The KSP will need to be given to you like an equilibrium constant, or vice versa. If you figure out these concentrations, if you know those concentrations, you can figure out the KSP. So that's going to be the same as a rice table. We'll look at that in class. Lastly, factors affecting solubility. This is, once again, that common ion effect. This is what I was talking about. If I'm trying to dissolve barium sulfate in a solution that already contains sulfate ions, the solubility will be decreased. Okay, you'll see less ability to dissolve barium sulfate. Even though there's no barium in solution, it doesn't matter. You can't dissolve barium without dissolving the sulfate also, right? The two of them go together. You can't just add sulfate ions to solution. You're adding the whole thing. I can't just add barium to solution. So that affects the solubility. The other effect is a pH effect. And that is for insoluble salts containing basic ions. Remember, we learned that fluoride ion is a basic ion. If you add sodium fluoride to the salt to water, you get a basic salt, right? So this is a basic ion. Solubility increases as the pH decreases. Because as the pH decreases, it means I'm adding this which means I could pull this out of solution and form this, which that's Le Chatelier's principle. Effectively, if I remove this from solution, that increases the solubility of this. And that's exactly what's happening, okay, when we have something like this. So we have this insoluble salt. We say it's insoluble. Everything's soluble to some extent, so it's not very soluble. But this increases its solubility, okay? And that's really all I have for the video. It's a shorter video, so I'll see you in class to discuss this material.